Hello students, let's continue our discussion on current electricity. This will be the last session of current electricity. And in the last session, the discussion was about one of the application and the fundamentals of potentiometer, right? We discussed about principle of potentiometer and we also discussed about one of the application, which is potentiometer is used to compare EMF of two cells, right? That is the first application which we discussed about. Moving ahead, let us go for the second application and see how can we make use of potentiometer in finding the internal resistance of a cell. Okay, so the second application is to find the internal resistance of a cell. Okay, so potentiometer can also be used to find the internal resistance of cell. Let us see how can we do that. Okay, as you all know, the potentiometer device looks somewhat like this. A lengthy wire connected to a battery of higher EMF with a variable resistor to control the current flow in the circuit. That's it. And from this point, you will have certain setup which is called secondary branch, and that secondary branch is again connected to the primary branch using a jack key, right? That's the basic structure of a potentiometer. Now in the last session, the first when we were discussing the first application, we had two cells connected in parallel in the secondary branch, and one cell is chosen at a time for the flow of current or in order to make the circuit balanced, and hence the galvanometer rates zero deflection. So one cell chosen at a time, and hence we got E1 is equal to E1 proportional to L1, E2 proportional to L2, right? And rest is the final conclusion was E1 by E2 is equal to L1 by L2, where L1 is the length at which for the first cell the galvanometer read zero deflection, and L2 is the length for which the galvanometer read zero deflection for the second cell. Now moving ahead, how do we find the internal resistance of a cell? To find the internal resistance of a cell, the circuit in the secondary branch is as follows. What we will have again is a parallel circuit with the cell whose internal EMF has to be calculated. Let E be the EMF of this cell, which should be known to us, and not necessarily. R is the internal resistance. Okay, E is the EMF, R is the internal resistance of this cell, and parallel to this circuit, parallel to this cell, we will have an external resistor connected whose resistance is R, and we will also have a key with that resistance, and both of them will have their terminals like this. And now what we will have from this point onwards is another terminal connected to galvanometer, and the galvanometer's other end going to jack key like this, which will slide on this. So now, these two terminals are connected. We can connect them in the beginning itself since we have the key. Okay, this is the circuit, complete circuit. A cell of EMF E and internal resistance R in parallel with an external resistance R with a key, all of them connected in parallel with the galvanometer in series, then, and the other end of the galvanometer connected to the jack key. Okay, this is the circuit to find the internal resistance of the cell given. And now, how do we find the internal resistance? In the first case, the key is open. Okay, when the key is open, as you can observe, now the current in the secondary branch would be only through this part of the circuit. Since the key is open, there will be no current in the upper branch of secondary circuit, right? So this part will not have any current in it, but this part can have the current. And now this is similar to what we discussed when it comes to the EMFs, comparing the EMFs. So this cell will push the current in the opposite direction, and this current will be trying to enter into the branch, and hence for a particular length, when the potential drop becomes equal to the EMF of the cell, okay, when the potential drop becomes equal to EMF of the cell, then the galvanometer reads zero deflection. Again, let L1 be the length for which galvanometer reads zero deflection when you have only the cell connected in the secondary branch of the circuit. Okay. So now what we can say is E1 proportional to L1, right? We can say so. Or if you want to keep it completely, you can also write it as E1. It's just E that we have, only one cell, no? So E proportional to L1. So, or you can also write E is equal to phi L1, where phi is the potential gradient. And now, okay, yeah, we can take E itself instead of V. You know that why? Because now there will be no current. There will be no current flowing in this part of the circuit. Current is zero, and hence E becomes equal to V. I gave this during the conclusion of the previous video, right? How did we take E instead of V? Because what we now get is potential difference, not the EMF, right? But E becomes equal to V because there is no current flowing through the given cell, right? So I can take directly that E is proportional to L1 certain length. Now in the next part, what we'll do is we will close the key. Key is closed. When the key is closed in the second case, now comes the interesting part. Then what happens is, even though there is no current entering this branch and leaving the branch, okay, because at certain length, once again, you will have the balancing, and hence galvanometer reads zero deflection. So let the length for that to be L2. And now you observe carefully, now you have certain current flowing in this part of the circuit, okay, through the, like they are all connected somewhat like a parallel series circuit, resistor, key and the cell. Now there is current in this part of the circuit, and there is no current entering the entire branch, and there is no current leaving the entire branch when the galvanometer reads zero deflection for a particular voltage or for a particular length of L2. Following? So there will be current in this branch. Current starts from here, certain current I, and this current, part of this current will manage the current that is trying to enter the secondary branch, and hence no deflection in the galvanometer. So this current will be maintained across the throughout this part of the circuit. So for certain length L2, we have uh, we have current which is I flowing through this part of the circuit, and the galvanometer is reading zero deflection. So now what we now have is, see, since there is current in the circuit and the circuit is closed, instead of E this time I should take V, TPD, terminal potential difference, across these two ends. Following? In the first case, when the key is open, there was no current in this part of the circuit, so I directly took E proportional to L1. But in the second case, key is closed, so the circuit is closed and hence there is current flowing through this circuit, and hence you will have TPD instead of EMF. That is what is the basic difference between TPD and EMF, right? EMF is the potential difference when the circuit is open as such, and TPD is the potential difference when the circuit is closed. So now this circuit is closed and hence what we get now is TPD instead of EMF. So when the key is closed, it is TPD voltage across these 2 points, and this voltage is same for both the resistor and the cell, right? The TPD is same for the cell and for the resistor because they are common. These 2 points are common for both the resistor and the cell. So it is V proportional to L2. Okay. So now I can write E by V is equal to L1 by L2. Right. How do we express E? When you are given with the EMF and internal resistance, the current in the branch will be given by I is equal to E by R plus R, right? Where R is the external resistance of the circuit and small r is the internal resistance of the cell, right? And E is the EMF of the cell. So now, according to this expression, E becomes equal to I times R plus R. And at the same time, what is V equal to? V is the potential difference between these 2 points, which can be expressed both in terms of the EMF, which is given by V is equal to E minus IR. This is also fine. And if you consider the upper part, you can also express simply by applying the Ohm's law for this resistor. Across the resistor, I can also write V is equal to I capital R IR, right? I can do that. So V is equal to IR across the resistor. So V is equal to IR is what I'll choose. Now replacing E by I of R plus R and V by IR, we will be left with I of R plus R divided by IR is equal to L1 by L2. Okay. So I and I cancels. What we are interested in is this small r, the internal resistance of the cell. So it is going to be R by R plus small r by R is equal to L1 by L2. This is 1, right? If you send that to the other side, R becomes equal to capital R times L1 by L2 minus 1. That's it. This is the expression for internal resistance of the cell given with the value of external resistance connected. This value should be known to us, okay? Capital R, the external resistance value. And then obviously we will get L1 and L2 during the experiment itself. L1 is the length when the key is open, L2 is the length when the key is closed. L1 corresponds to EMF of the cell because the key is closed, the key is open and hence no current in the circuit. L2 corresponds to voltage across the cell or TPD across the cell because the key is closed and there will be current in this part of the circuit. So we took E proportional to L1, V proportional to L2 and the ratio is as follows, and this is the final expression for the internal resistance of the cell expressed in terms of external resistance. This external resistance, we will decide the external resistance value, what resistance should be placed there, connected there. So that value is easy to obtain. L1 and L2 are the lengths for which the galvanometer reads zero deflection First for uh, the open key circuit, and yet excuse me, L2 is the length for which the galvanometer reads zero deflection. For the closed circuit, okay, so this is the expression, and that is how we find the internal resistance. Thank you. Again, this question, both the explanation of first application, explanation of first application and the explanation of second application, this uh, are not asked for your board examination. Okay, they are not the standard questions, but the conceptual understanding will help you for the competitive exams. Okay.